Look up at the Pleiades, that sparkling little group in the night sky. Those stars are not random neighbors. They are a family, bound together for millions of years in a dense cosmic gathering called a star cluster. For a long time, we thought these clusters were simple and predictable, just ancient collections of similar stars. We were completely wrong. Hidden within these glittering islands are secrets that challenge the very laws of physics and rewrite the story of our universe. By the end of this journey, you will know 25 of the strangest discoveries ever made about star clusters, revelations that include cosmic cannibals, missing black holes, and stars that simply should not exist. How can a star appear younger than all its siblings? What invisible monster hides at the heart of the brightest cluster? We are about to dive deep into a cosmic mystery that turns everything we thought we knew upside down. What do you think is the most surprising thing a star cluster could hide? The first mystery is one that stares back at us from the very oldest neighborhoods in the galaxy. Inside ancient globular clusters, every star was born in the same colossal burst of creation, billions of years ago. They should all be aging gracefully together, cooling down into red giants or fading into dim dwarfs. Yet, scattered among these elderly populations are rebels. They burn with a fierce, hot blue light, appearing impossibly youthful and vibrant against their ancient backdrop. Astronomers call them blue stragglers, and their very existence is a blatant violation of the rules of stellar evolution. How can a star be younger than its own family? It is like finding a toddler playing in a retirement home. The leading theory is as dramatic as it sounds: cosmic violence. In the densely packed core of a globular cluster, stars are not the distant, solitary points we see from Earth. They are crowded together, a celestial mosh pit where gravitational encounters are frequent and chaotic. Sometimes, two stars will collide in a catastrophic merger, combining their fuel into a single, more massive and hotter star. This newly forged object looks blue and young because, in a way, it has been reborn. Another possibility involves binary star systems, where one star siphons material from its companion, bulking up and reigniting its nuclear fires. The iconic globular cluster 47 Tucanae is a perfect laboratory for this phenomenon. Observations from the Hubble Space Telescope have mapped its core, pinpointing these brilliant blue stragglers. They are not where we would expect young stars to form. They are right in the heart of the old crowd. This discovery forced astronomers to accept that star clusters are not peaceful retirement communities, but dynamic arenas where stars can literally crash together and steal life from one another, rewriting their own destinies long after they were born. But blue stragglers are not the only violent residents in these dense stellar cities. To uncover the next secret, we must travel to the most spectacular globular cluster visible from Earth, Omega Centauri. This glittering sphere contains millions of stars, so many that it appears as a fuzzy patch of light to the naked eye. For centuries, it was considered just another, albeit enormous, star cluster. Yet something about it never quite fit. Its stars are not all the same age or chemical composition, which is highly unusual for a globular cluster. This led to a radical theory: Omega Centauri is not a cluster at all. It is the stripped-down heart of a small galaxy that was devoured by our Milky Way long ago, a galactic core that survived the collision. And at the very center of this ancient wreckage, astronomers found evidence of a monster. By meticulously tracking the motions of stars near the cluster's core with the Hubble Space Telescope, they noticed something bizarre. A group of stars was whipping around at incredibly high speeds, as if caught in the grip of an invisible whirlpool. The only thing that could explain such frantic orbital dance is an immense gravitational anchor, an object with the mass of about 40,000 suns, crammed into a region of space smaller than our solar system. That object is an intermediate mass black hole. This discovery sent shockwaves through astronomy because this type of black hole is the universe's great missing link. We know of small black holes, the remnants of dead stars a few times the mass of our Sun, and we know of the supermassive behemoths, millions or billions of solar masses that lurk in the centers of galaxies. But the middle ground, the black holes weighing thousands of suns, had remained elusive. Omega Centauri's hidden giant is a direct clue, suggesting these intermediate monsters might form in the dense cores of dwarf galaxies or, as in this case, within the cannibalized remains of them. Its presence fundamentally reshapes the entire cluster's dynamics, acting as a gravitational puppet master that stirs the orbits of millions of stars over cosmic time. The existence of such a monstrous black hole forces us to reconsider everything about these environments, including what can survive within them. For decades, astronomers held a firm belief: planets could not possibly form in the chaotic, radiation-filled cores of globular clusters. The gravitational shoves from passing stars would rip apart the delicate disks of dust and gas that birth planets, or fling any fledgling worlds into the void. This assumption was shattered by a single, ancient world with a story of unimaginable survival. In the globular cluster Messier 4, a planet orbits not one but two dead stars, a pulsar and a white dwarf. This world, known as PSRB 1620-26b, has earned the nickname Methuselah. It is roughly 2.5 times the mass of Jupiter and is believed to be nearly 13 billion years old, making it one of the oldest planets we have ever detected. Its very existence is a cosmic miracle. This planet likely formed around a sun-like star, then watched as that star died in a violent supernova, somehow remaining bound to the resulting neutron star. Later, another star entered the system, aged, and became a white dwarf. The planet endured it all, a silent witness to the most catastrophic stellar events imaginable, all while being jostled by the gravitational tides of hundreds of thousands of neighboring stars. Its persistence proves that planets are far tougher and planet formation far more versatile than we ever dreamed. If a world can survive this, where else might they be hiding? The answer came from a much younger stellar neighborhood. The Beehive Cluster, a beautiful open cluster visible to the naked eye, is a bustling stellar nursery about 600 million years old. Using data from the Kepler Space Telescope, astronomers confirmed the presence of multiple planets there, worlds orbiting sun-like stars in relative peace. This discovery was crucial. It demonstrated that the planet-forming process is not a fragile, rare event, but a robust and common one, capable of proceeding even in a busy cluster environment. Now picture the sky from the surface of such a world. Our single sun would be replaced by a dazzling, permanent celestial spectacle. Hundreds of stars, many brighter than Venus appears from Earth, would dot the heavens day and night. Some would be close enough to cast faint, multiple shadows, and the concept of true darkness might not exist. The survival of planets in these hostile neighborhoods opens a thrilling new chapter in the search for life, suggesting that even the most crowded corners of the galaxy could host alien worlds with skies of breathtaking beauty. These ancient planets prove that even delicate worlds can survive the chaos, but not all stars choose to stay. Some are violently evicted, becoming cosmic fugitives racing across the galaxy. These are hypervelocity stars, stellar cannonballs flung from their dense home clusters at speeds so great they can escape the Milky Way's gravity entirely. Their origin story is one of the most dramatic events in the universe. Picture a tight binary star system orbiting in the crowded core of a massive cluster. One of the stars reaches the end of its life and explodes as a supernova. If the explosion is slightly off-center, the surviving companion can be kicked away like a stone from a sling, rocketing outward at over 1 million miles per hour. Another method involves a close gravitational encounter with a binary black hole system in the cluster's heart, a celestial slingshot of unimaginable power. We have observed these runaways in the Tarantula Nebula, home to the colossal young cluster R136. Astronomers have tracked stars that seem to be fleeing the scene. They travel so fast they plow through the thin gas between stars, creating a visible bow shock, a glowing wave in space, much like the wake in front of a speeding boat. These bow shocks are the telltale signatures of their incredible journeys. For scientists, these runaway stars are more than just curiosities, they are invaluable probes. By tracing their paths backward across the sky, we can potentially pinpoint the violent event that launched them, offering a forensic look at the extreme physics of cluster cores. Their trajectories also map the hidden gravitational landscape of the galaxy, as their paths are bent by the dark matter we cannot see. Each one is a message in a bottle, hurled from the most turbulent neighborhoods in the cosmos, carrying with it the secrets of its explosive birth. The survival of hypervelocity stars hints at the immense forces at work in a cluster's heart, but the very age of some clusters presents an even deeper puzzle. We find star clusters that should not be so old, existing in places where they have no right to be. This mystery unfolds in the faint, ghostly dwarf galaxies that orbit our Milky Way. Take the Fornax dwarf spheroidal, a small, diffuse smudge of stars about 460,000 light-years away. It is a modest galaxy with relatively few stars spread out over a large volume. Yet, orbiting this unassuming cosmic backwater are 6 brilliant, dense globular clusters. These clusters are not just old, they are ancient, dating back nearly to the dawn of the universe itself, over 13 billion years. This creates a profound contradiction. How can such a small, faint galaxy, which seems to have had a quiet and uneventful life, host these magnificent, ancient stellar jewels? It is like finding a collection of priceless Renaissance masterpieces in a simple, modern cabin. The prevailing theory of galaxy formation suggests that large structures like the Milky Way grew by consuming smaller ones. In that violent process, the dense globular clusters from the devoured galaxy should have been torn apart and absorbed. The fact that Fornax's clusters remain intact, orbiting their small host, suggests 2 startling possibilities. Perhaps these clusters did not form within the Fornax dwarf at all. Instead, they could be the stripped cores of even earlier, smaller galaxies that Fornax itself cannibalized long ago, making this faint dwarf a silent predator with a hidden history. Or, even more challenging to our models, these immense clusters formed in situ, right inside this tiny galaxy, during a burst of furious star formation in the universe's first billion years. If true, it means the conditions to create these dense stellar cities existed almost everywhere, even in the smallest galactic fragments. This discovery forces astronomers to reconsider the timeline of cosmic structure. Did the very first lights in the universe flicker on in colossal clusters that formed before the galaxies we see today even took shape? The ancient clusters of Fornax are silent, glittering relics from that forgotten era, holding secrets about how the first pieces of the cosmic web were woven together. Those ancient clusters hold more than just stars, they hold a census of stellar life and death. Yet when astronomers take that census, they find someone is missing. In the careful accounting of stars within certain globular clusters, a specific group fails to appear in the expected numbers. These are the red giants, the swollen, brilliant final act for stars like our Sun. According to the well-established roadmap of stellar evolution, a predictable percentage of an old cluster's stars should be in this luminous red giant phase at any given time. But in clusters like Messier 4, the count comes up short. Where did the giants go? This is the missing red giants problem, a quiet anomaly that suggests our understanding of a star's final chapters is incomplete. The journey to becoming a red giant is a slow, inevitable process. After billions of years burning hydrogen in its core, a star like our Sun exhausts that fuel. The core contracts and heats up while the outer layers expand outward, cooling and reddening into a monstrous, luminous balloon. This phase is a brief but brilliant farewell, a star's last hurrah before it sheds its outer layers and collapses into a white dwarf. In the peaceful isolation of space, this process is clockwork, but in a globular cluster, the rules change. One theory points to stellar theft. In the dense core, a red giant's bloated, loosely held outer atmosphere is vulnerable. A close encounter with another star or the relentless tidal pull of the cluster's collective gravity could strip away these outer layers prematurely. It is like a fruit being peeled by an invisible hand before it is fully ripe. This enhanced mass loss would expose the star's hot helium core earlier than expected, causing it to skip the full, bright red giant stage and move directly to the next, less luminous phase of burning helium. The giant would not truly vanish but transform into something else on the ledger, masquerading as a different type of star. Another possibility is far more dramatic: eviction. The same gravitational encounters that can create blue stragglers might also be kicking elderly stars out of the nursing home. As a star evolves into a red giant, its mass distribution changes, potentially making its orbit unstable within the complex gravitational dance of the core. A particularly close gravitational slingshot could eject the aging star entirely, flinging it into the cluster's outskirts or even into the galactic halo, where it would fade from the central census. This means the serene, glowing red giants we picture in these clusters might not be serene at all. They could be living on borrowed time, constantly at risk of having their outer layers stolen or being thrown out into the cold darkness of interstellar space. This missing population forces a profound reconsideration. We must view a star's life not as a solitary destiny, but as a story shaped by its community. In the crowded metropolis of a globular cluster, even a star's death can be interrupted, accelerated, or violently redirected by its neighbors. The quiet disappearance of red giants is just one clue that a star's life in a cluster is far from simple. But to uncover the deepest secret, we must look not at how these stars die, but at how they are born. For generations, astronomy textbooks held a simple, elegant truth: a globular cluster is a single, pristine burst of creation. Every star within it condensed from the same giant cloud of gas at the same moment in cosmic history, making them all identical chemical siblings. This was the foundational belief. And it is completely wrong. The truth is far more complex, and it was revealed by peering into the very hearts of these clusters with a powerful tool: spectroscopy. By splitting the light from individual stars into a rainbow spectrum, astronomers can read the unique chemical fingerprints imprinted in that light. When they did this to stars in classic globular clusters, they expected to see the same signature everywhere. Instead, they found a family with a hidden, divided history. Take the massive cluster NGC 2808. Its stars, when viewed through a telescope, appear as a uniform, ancient swarm. But spectroscopic analysis tells a different story. It reveals at least 3 distinct generations of stars, all within the same gravitational family. The first generation shows the expected, primordial mix of hydrogen and helium with just a sprinkle of heavier elements, but the second and third generations are chemically enriched. They show higher levels of helium, nitrogen, and sometimes sodium. This is a cosmic paradox. How can younger stars exist inside a structure that supposedly formed all its stars at once over 12 billion years ago? The explanation points to a dramatic and messy childhood. After the first massive stars of the initial generation ignited, they did not just shine, they pollute. Some of these early giants lived fast and died young in colossal supernova explosions, seeding the remaining cluster gas with new, heavier elements forged in their cores. Others, known as asymptotic giant branch stars, blew off their outer layers in powerful winds, lacing the environment with helium and nitrogen. Crucially, the cluster's immense gravity was strong enough to hold onto much of this enriched gas, preventing it from being blown entirely into deep space. This polluted material then cooled, collapsed, and ignited a second wave of star formation millions of years after the first. These new stars were born from a different recipe, carrying the chemical legacy of their deceased elders within them. This discovery shatters the old, simple definition. A globular cluster is not a single snapshot of star birth. It is a multi-generational saga. It is a cosmic ecosystem that can retain its own raw materials, recycle the ashes of its dead, and give birth to new stars with different chemical identities, all within its own tightly bound domain. This complexity forces us to see these ancient objects not as simple relics, but as dynamic factories with a rich and layered history, where the story of creation happened not once, but in successive, distinct chapters. This chemical split between generations is not just a minor detail, it is a profound signature of violence written in starlight. The specific pattern of enrichment is the key clue, a strange overabundance of sodium and aluminum, paired mysteriously with a depletion of oxygen and magnesium. This is not the chemical fingerprint of a typical supernova. It points to a much more specific and slower kind of alchemy, a process called proton capture nucleosynthesis. This happens deep within stars where the core temperatures are scorching but not catastrophic. Under these intense conditions, atomic nuclei can capture extra protons one by one, slowly transforming one element into another. An oxygen nucleus, for instance, can capture protons and gradually become neon, sodium, and eventually aluminum. Meanwhile, magnesium can be transformed into aluminum as well. So the stars showing this signature, the later generations, are literally built from ashes where oxygen and magnesium were burned away to create sodium and aluminum. But this creates a new detective story. Where did this uniquely processed material come from? It had to be forged inside a previous generation of stars and then expelled into the cluster's nursery. The leading suspects are not the titans that die in supernova blasts, but a different class of star altogether, intermediate mass stars between about 4 and 8 times the mass of our Sun. These stars take a quieter but no less dramatic exit. They never experience the core collapse of a supernova. Instead, in their final, unstable throes as asymptotic giant branch stars, they become cosmic bellows. They puff out slow, dense winds of gas from their bloated surfaces, winds that are rich with the products of that internal proton capture process. This material is not blasted into deep space at incredible speeds. It is shed gently like a cosmic mist, and because it is moving relatively slowly, the cluster's strong gravity can easily capture and hold onto it. This polluted gas then swirls together with any remaining pristine hydrogen and helium, creating the perfect recipe for that second generation of chemically peculiar stars. So the great gender mystery, this division between stellar siblings, is solved by this quiet, persistent pollution. The first generation of massive stars acted as the cluster's first chemical factories, and their slower, wind-shedding cousins provided the specific enriched ingredients that made the second generation so distinct. It reveals that a star cluster is a true ecosystem, capable of internal recycling on a grand scale, where the life and death of one generation literally forms the building blocks of the next. This chemical recycling within clusters paints a picture of a self-contained world, but that world exists within a much larger cosmic structure held together by an invisible force. Yet when we look for that same force inside globular clusters, we find a startling absence. The universe is dominated by dark matter, the mysterious, invisible substance that provides the gravitational scaffolding for galaxies. Its presence is felt in the way stars orbit the centers of galaxies much too fast for the visible matter alone to hold them. So, logically, the massive, ancient globular clusters orbiting our galaxy should also be embedded in their own halos of this dark stuff. The measurements, however, tell a different story. Take the giant cluster Omega Centauri again. By meticulously tracking the speeds of stars at different distances from its core, astronomers can calculate the total mass needed to keep those stars from flying apart. The result is striking. The calculated mass matches almost perfectly the mass we can see in the form of all its millions of shining stars. There is no significant extra mass, no hidden reservoir of dark matter holding the cluster together. Its own stellar gravity is sufficient. This is profoundly different from a galaxy where the visible stars account for only a tiny fraction of the gravity required. So why would these colossal stellar cities lack the dark matter that seems to be everywhere else? Two compelling theories emerge, each telling a different story about the cluster's origin. The first suggests these clusters were simply born in the wrong neighborhood. In the early universe, dark matter and normal matter were not perfectly mixed. Dense knots of pure gas, perhaps forming in the turbulent wakes of colliding gas clouds, could have collapsed under their own gravity to form stars without a significant dark matter component from the start. They would be islands of visible matter in a dark matter sea. The second theory is more violent. Perhaps globular clusters did form with dark matter halos like miniature galaxies, but those halos were stolen. Over billions of years, as the cluster orbits through the immense dark matter halo of the Milky Way, the repeated gravitational tug-of-war, a process called tidal stripping, could have slowly but completely ripped away the cluster's diffused dark matter cloak, leaving only the dense, resilient core of stars behind. This would make globular clusters the bare, skeletal remains of something that was once much larger. The mystery deepens with the discovery of a new class of objects, faint, diffuse clusters that seem to blur the line. Systems like Palomar 5 are incredibly sparse, with stars so widely spaced they should have dissolved into the galaxy long ago. Yet they persist. Their survival hints that they might be held together by something we cannot see. Perhaps a small, stubborn nugget of dark matter at their core, acting as a gravitational anchor. This keeps the question tantalizingly open. Are globular clusters the rare cosmic structures that somehow formed without the universe's dominant ingredient? Or are they the survivors of a brutal gravitational battle, standing as stark evidence of the Milky Way's destructive appetite? Their silent orbits hold the answer to how the visible and invisible cosmos interact. The absence of dark matter in many clusters may be the result of a long, slow demolition. Our galaxy is not a static museum, but a living, devouring beast, and the glittering clusters that orbit it are not immune. They are being slowly torn apart before our eyes. This process, galactic cannibalism, leaves behind ghostly evidence in the form of tidal tails. These are spectacular, ribbon-like streams of stars, flung from a cluster by the Milky Way's immense gravitational tides. The most stunning example is Palomar 5. This ancient, faint globular cluster is on a death spiral. As it orbits, our galaxy's gravity pulls more strongly on the near side of the cluster than the far side, stretching it like taffy. The result is two immense, graceful tails of stars that lead and follow the cluster in its orbit, each stretching for over 20,000 light-years across the sky. Palomar 5 is not a dense sphere anymore, it is a smudge with long, luminous scars. These streams are more than just destruction, they are forensic evidence. Each star in that stream is a tracer bullet, following the precise path dictated by the galaxy's gravitational field. By mapping the exact positions and motions of these stars with missions like the Gaia Space Observatory, astronomers can perform a cosmic autopsy. The shape and speed of the tidal tail tells a precise story. It reveals the total mass of our galaxy, including the vast, invisible dark matter halo that envelops it. Think of it like this: the stream of stars is a probe dropped into the ocean of dark matter, and its drift shows us the strength and shape of the unseen currents. Furthermore, these streams are historical records. Many star streams in our galactic halo no longer have a visible cluster at their center, just a river of orphaned stars. These are the dissolving remains of clusters or small dwarf galaxies that the Milky Way consumed billions of years ago. Their stars are now fully assimilated, but they still move together like a school of fish, preserving the memory of their original home. By finding and decoding these ghostly rivers of light, we are literally reading the Milky Way's violent autobiography, chapter by chapter, merger by merger. Galactic cannibalism may be a slow process, but the birth of a new generation of clusters is a spectacle of raw, violent creation. Far from the serene ancient globulars, the universe still forges stellar cities of staggering scale in the most extreme environments imaginable. These are superstar clusters, and they are born from chaos. When two galaxies collide in a slow-motion cosmic dance, their vast reservoirs of gas are violently compressed. This triggers an eruption of star formation so intense it is called a starburst, and within that firestorm, superstar clusters ignite. The antennae galaxies, a pair of spiral galaxies locked in a titanic merger about 45 million light-years away, provide the perfect cosmic laboratory. Images from the Hubble Space Telescope reveal the aftermath not as destruction, but as a frenzy of creation. Scattered across the tangled wreckage of the galactic collision are not just individual new stars, but hundreds of brilliant blue-white knots of light. Each knot is a superstar cluster, a single object containing the mass of millions of suns packed into a region just a few light-years across. They are so bright and so dense that, from a distance, a single cluster can outshine an entire small galaxy. These are not merely large open clusters, they are the potential seeds of future globular clusters, caught in the very first moments of their existence. Their sheer mass is the key to their potential destiny. A typical open cluster, like the Pleiades, has a gravitational grip too weak to withstand the tidal forces of the galaxy and the gravitational kicks from passing gas clouds. Over a few 100 million years, they gently dissolve, but a superstar cluster with the mass of a small galaxy itself has a far stronger gravitational anchor. The million solar mass behemoths being forged in the antennae galaxies could, in theory, hold themselves together for 10 billion years or more. This presents astronomers with a thrilling, real-time experiment. We are witnessing the possible birth of globular clusters in the modern universe. The critical question now is one of survival. Will these brilliant young clusters manage to retain enough of their gas and stars as the merger subsides and the galactic environment calms? Or will the very violence of their birth also be their undoing, with supernova explosions from their most massive members blasting away the material that binds them? By studying these infant giants, we are getting a front-row seat to a process that was commonplace in the early cosmos, watching as the universe attempts to build its next generation of ancient, glittering islands. The violent births of superstar clusters show creation on a cosmic scale, but the death of a single star can leave behind a world of impossible beauty. Deep within the ancient globular cluster M53, a dead star ticks with the precision of an atomic clock. It is a pulsar, the spinning, magnetized core of a massive star that ended its life in a supernova. As it spins, it beams a lighthouse-like pulse of radio waves toward Earth with metronomic regularity. Yet astronomers listening to this cosmic tick noticed a faint but consistent wobble in its rhythm. Something with gravity was tugging on the pulsar, ever so slightly pulling it back and forth. That something is a planet, but not a world of rock and iron like our own. This is a world forged in the most extreme furnace imaginable, a place that could be composed largely of crystallized carbon, a planet-sized diamond orbiting its dead host. The discovery method itself is a marvel of precision. By tracking the exact arrival time of the pulsar's radio pulses over months and years, scientists can detect variations as small as a few millionths of a second. Any rhythmic delay or advance in the pulse timing betrays the gravitational influence of an unseen companion, its mass and orbit revealed in the heartbeat of the dead star. But how did a planet survive the supernova that created the pulsar, and what could it possibly be made of? The leading theory is as dramatic as the world it describes. The planet is likely the corpse of a star itself. Imagine a binary system where two stars once danced. One was more massive, evolving faster and exploding, leaving behind the pulsar. Its companion, a carbon-rich giant star, was then subjected to a relentless assault. The intense radiation and particle winds from the newborn pulsar acted like a cosmic sandblaster, violently stripping away the giant star's outer layers of hydrogen and helium. What remained was the star's exposed core, an object rich in carbon and oxygen, now robbed of its gaseous envelope. This stripped core, still massive enough to be planet-sized, is what we detect today. Its composition would be utterly alien. Under the immense pressures of its own gravity, the carbon in its interior could have crystallized into a lattice structure, forming a layer of diamond hundreds or thousands of miles thick. Mixed with oxygen, it might also have vast substrates of solid oxygen or other exotic crystals. This is not a world with mountains of rock, but of gemstone. A landscape, if one could stand on it, might glitter with crystalline structures under the eerie, strobing light of its pulsar sun, a place where the very ground is the remnant heart of a murdered star. It stands as one of the most bizarre and magnificent discoveries, proving that even in the graveyards of ancient clusters, new and unimagined forms of worlds can be born from destruction. The diamond worlds orbiting dead pulsars are forged from stellar corpses, but the story of star clusters is not only about ancient relics and violent ends. It is also about vibrant, youthful giants that defy our timeline. For decades, the rule seemed absolute. Globular clusters are fossils. They are the exclusive products of the universe's chaotic infancy over 10 billion years ago. This assumption has been spectacularly overturned. Scattered throughout our galactic neighborhood within satellite galaxies like the Large Magellanic Cloud, we find massive, dense, spherical clusters that look for all the world like classic globulars, except they are dazzlingly young. NGC 1866 is a perfect example. Through a telescope, it appears as a magnificent, tightly packed sphere of stars, indistinguishable from the ancient globulars orbiting the Milky Way. Yet its stars blaze with a hot, blue-white light, and detailed analysis reveals its true age, a mere 100 million years old. To put that in perspective, when dinosaurs ruled the Earth, this cluster did not yet exist. Its stars are cosmic newborns. This discovery shatters a fundamental paradigm. The universe did not stop making these immense stellar cities after its first few billion years. The recipe for creating a massive, gravitationally bound cluster is not a lost art of the early cosmos. It is a process that can and does still occur, given the right conditions of dense, cool gas and a triggering event, like a galactic interaction or a local shockwave. These young globulars, sometimes called blue globular clusters, are a gift to astronomers. They provide a nearby laboratory, a chance to observe in high definition what the ancient globulars were like in their first 100 million years of life. We can study their internal dynamics, watch how their most massive stars evolve and die, and see if stellar collisions are already beginning to create blue stragglers. We can witness in real time how the fierce radiation from brilliant young stars blows away the leftover gas from their formation, a process that ultimately determines the cluster's final shape and stability. NGC 1866 and its siblings are living proof that the cosmos is still capable of grand, organized construction on a scale we once thought was reserved for the distant past. They are not fossils, they are thriving metropolises, and their existence forces us to rewrite the guidebook on how and when the universe builds its most spectacular stellar communities. The vibrant young clusters prove star formation is an ongoing art, but the densest ancient cores have perfected a far more destructive craft. Within the gravitational chaos of a globular cluster's heart, stellar mass black holes are not lonely ghosts, they are social creatures. These environments are perfect factories for creating binary black holes, pairs of invisible monsters locked in a lethal dance. Here is how the factory works. When massive stars die, they leave behind black holes. In the crowded core, these black holes, being the heaviest objects, naturally sink toward the center through a process called dynamical friction, like heavy stones sinking in water. With so many of them in a small volume, gravitational encounters are inevitable. A close pass between two single black holes can easily bind them together into a binary system, a partnership forged not by birth but by chaotic circumstance. Once paired, their story accelerates. As they orbit each other, they ripple space-time itself, emitting gravitational waves, which are faint ripples in the fabric of the cosmos. This emission saps energy from their orbit, causing them to spiral inward, closer and closer, over millions of years. The final act is a merger, a violent collision that releases more energy in a fraction of a second than all the stars in the observable universe combined. This theoretical process moved from speculation to confirmed reality with the groundbreaking detections by the LIGO and Virgo observatories. These instruments have listened to the cosmic symphony of space-time and heard the distinctive chirp, the rising frequency, of multiple black hole mergers. Statistical analysis of these events suggests several likely originated not in isolated galactic fields, but within the dense stellar cities of globular clusters. The clues are in the masses and spins of the merging black holes. Some pairs are surprisingly massive or have spins that are misaligned, hinting at a violent courtship through dynamical capture rather than a peaceful binary evolution from a twin star system. This transforms our view of these ancient clusters. They are not just serene collections of old stars, they are cosmic engines, continuously forging and firing the most energetic events we can detect. Each merger detected is a message from one of these factories, a signature of the relentless gravitational physics churning in the darkness at the heart of a glittering sphere. Even the orderly timeline of a star's life becomes blurred in these dense communities. When astronomers point the Hubble Space Telescope at intermediate-age star clusters, those a few hundred million to a couple billion years old, they see something strange in the very data that usually tells a star's age. It is called the main sequence turn-off point. On a graph plotting a star's color against its brightness, most stars spend their lives on a neat diagonal band known as the main sequence. When a star exhausts the hydrogen fuel in its core, it begins to leave this band, turning off to become a red giant. In a simple, single-birth cluster, every star should leave the main sequence at nearly the same point, creating a sharp, clean break in the data. But Hubble reveals a profound enigma. In clusters like NGC 1846, the turnoff is not sharp. It is broad, fuzzy, and smeared out, as if the stars are departing the main sequence at different times or under different conditions. This blur challenges a core assumption that all stars in a cluster are perfect twins, born together from the same cloud. The smeared turnoff suggests one of two things. Either the cluster's stars are not all the same age, with star formation trickling on for tens of millions of years longer than we thought possible, or something else is dramatically altering how these stars appear. The leading culprit is stellar rotation, and its effects are more powerful than anyone predicted. A star spinning rapidly at its equator bulges outward. This changes its internal structure, affecting how heat moves from its core to its surface. A fast-spinning star can appear cooler and redder at its equator than at its poles, and its overall brightness and color as seen from afar become a complex average of its entire spinning surface. Crucially, to our telescopes, a rapidly rotating star can masquerade as an older, cooler star. It mimics the very signal we use to date stellar populations. So that fuzzy turnoff might not be an age spread at all. It could be a rotation spread. It means that within the same cluster, born from the same gas, one star could be spinning lazily while its neighbor is a whirling dervish, each presenting a completely different face to the universe. This revelation forces a massive recalibration. To understand these clusters, we can no longer just measure light. We must now untangle the hidden physics of spin, a variable that was once considered a minor detail but now stands as a major player in the cosmic story of stellar evolution. The blurring of stellar timelines leads to an even more profound ambiguity, one that exists not within a cluster but in the vast, empty darkness between galaxies. Drifting through the cosmic voids are ghostly islands of light with no home. These are ultra-compact dwarf galaxies and orphan globular clusters, stellar systems so isolated they challenge our very definitions. Take the object known as Sucked 1. It contains tens of millions of stars packed into a region only about 200 light-years across, making it far denser than any typical dwarf galaxy, yet more massive and complex than any known globular cluster. It is a cosmic chimera, an object caught perfectly between two categories, and it floats utterly alone in intergalactic space. How did it get there? The answer is written in violence. During the colossal, slow-motion collisions between large galaxies, the tidal forces are unimaginable. They can act like cosmic hands, reaching into a galaxy's collection of globular clusters and dwarf satellite galaxies and violently plucking them out. The gravitational tug of war does not just stretch these objects, it can completely sever their connection, flinging them out into the blackness at high speeds. These orphaned systems then embark on an eternal journey through the void, carrying with them the unmistakable signature of a galactic catastrophe that happened billions of years ago. Their isolation makes them pristine laboratories, with no galactic neighbor to distort them or no reservoir of gas to spark new star formation. They remain frozen in time, preserving the exact stellar population and chemical makeup they had at the moment of their ejection. Studying them is like examining a piece of shrapnel from an ancient explosion. It tells us about the force and angle of the impact. Their very existence redraws the map of cosmic structure. We used to think of galaxies as islands in a dark ocean, each with its own retinue of clusters orbiting loyally. But these lonely wanderers reveal a universe where the islands themselves are constantly at war, and their glittering treasures are often scattered into the deep. They are the lost children of galactic collisions, and by tracing their paths backward, we can begin to reconstruct the epic battles that shaped the galactic neighborhood we see today. The lonely wanderers between galaxies hold their chemistry like a sealed letter, but inside the ancient clusters themselves, a specific element is missing from the cosmic mail. This is the lithium problem, a quiet but profound chemical mystery. Lithium is the third lightest element in the universe, forged in the frantic first minutes after the Big Bang alongside hydrogen and helium. Based on our models of that primordial fire, we can predict how much lithium should have been present in the gas that formed the first stars. Yet when astronomers measure the lithium content in the ancient, sun-like stars of old globular clusters, the numbers do not add up. The observed levels are often 2 to 3 times lower than the Big Bang predictions. It is as if someone went through the universe's oldest stellar libraries and systematically erased this one light element from the pages. Where did the lithium go? Two compelling and conflicting theories attempt to solve the case. The first suggests the stars themselves are the culprits. As a sun-like star ages, the convection currents in its outer layers act like a giant elevator, carrying material from the surface down into the hotter interior and back up. Lithium is a fragile element. At the relatively modest temperatures found in a star's interior, around 2.5 million degrees, lithium nuclei are destroyed, fused into heavier elements. If the convective zone in these old cluster stars reaches deep enough to dip into these warmer layers, the lithium gets burned away over billions of years. The star essentially digests its own primordial lithium. The second theory is far more radical. It proposes the clusters were born deficient. Perhaps the gas clouds that collapsed to form these ancient globular clusters were not perfectly pristine. They might have been pre-processed, already seeded by an earlier generation of massive, short-lived stars that formed and died even before the clusters we see today. These POP3 stars, as they are called, could have burned through their lithium and then polluted the cluster-forming gas with their lithium-depleted ashes. If true, it means the Big Bang lithium we think we understand was already being altered in pockets of the universe before most stars even ignited. To crack this mystery, astronomers turn to clusters of different ages. By measuring lithium in younger open clusters where stars have had less time to destroy it internally, they can establish a baseline. The results are startling. Even in some very young clusters, lithium levels can be lower than expected. This suggests the destruction mechanism is efficient and begins early, supporting the stellar digestion theory. However, the pattern is not uniform across all stars, even within the same cluster, hinting at complex internal processes tied to a star's rotation, magnetic activity, and precise internal structure. The lithium problem is more than a bookkeeping error for a light element. It is a direct probe into the hidden machinery of stars, a way to test our models of how material mixes and burns inside them over cosmic time. Furthermore, it challenges our understanding of the universe's first chemical moments. By studying this missing lithium, we are not just looking at a star's composition. We are attempting to read a history that was written in the first 3 minutes of existence and then partially erased over the next 13 billion years. The precise ticking of pulsars and the fading of lithium both rely on our ability to measure stars with perfect accuracy, but a single, subtle bend in the data threatens to undermine it all. Within every ancient star cluster, there exists a predictable pattern in the population, a census of how many stars shine at each level of brightness. This is the luminosity function. For old clusters, this graph takes a very specific shape, rising steadily as you look at fainter and fainter stars until it hits a distinct bend, a knee. This knee marks the point where the lowest mass stars, the tiny red dwarfs, begin to leave the main sequence after their extraordinarily long lives. Its position is a fundamental benchmark, a cosmic signpost that tells us the cluster's distance and the age of its faintest members with remarkable precision. But the universe, as always, loves an anomaly. In several well-studied globular clusters, including the magnificent 47 Tucanae, the knee is not where our best models say it should be. It appears shifted, as if the entire population of faint stars is either brighter or dimmer than expected. This is a quiet crisis in stellar demographics. If the knee is in the wrong place, one of our core assumptions is wrong. The first suspect is distance. We measure the distance to clusters using the apparent brightness of specific, well-understood stars. If we have misjudged that distance, even by a small percentage, it would systematically shift the entire luminosity function, moving the knee. A second, more profound possibility is that our models for how the smallest, coolest stars evolve are incomplete. These red dwarfs burn their hydrogen fuel so slowly and possess such complex interior dynamics that a small error in our physics could mean we are predicting their brightness incorrectly for a given age. The most intriguing explanation, however, points back to the great chemical divide within clusters. Remember those second-generation stars enriched with extra helium from their ancestors. Helium is a heavier element than hydrogen, and a star rich in helium behaves differently. It has a hotter, denser core, which makes it burn brighter and bluer for its mass. A population of helium-rich stars would therefore masquerade as being more massive or younger than they truly are. If a significant fraction of the faint stars in a cluster's knee region are secretly helium-enriched, they would glow more brightly than our standard models predict, effectively shifting the knee's position and fooling our measurements. This tiny bend in a graph is therefore a magnifying glass. It forces us to question not just one thing, but three: the vast scales of the galaxy, the hidden lives of the smallest stars, and the lasting chemical pollution from a cluster's violent youth. A single misplaced data point becomes a doorway into a much deeper mystery about the very ingredients of stellar life. The faint, flickering light of a star's final moments may hold the key to the most brilliant flashes in the cosmos. Among the most explosive mysteries of modern astronomy are fast radio bursts, millisecond-long blasts of radio energy so powerful they can outshine entire galaxies. For years, their origins were completely unknown, cosmic ghosts that vanished before we could trace them. Then a breakthrough came from an unlikely place. One of the first repeating fast radio bursts ever discovered, FRB 201800916b, was finally pinpointed. It did not come from the void between galaxies, but from a very specific neighborhood, a star-forming region within a small, turbulent dwarf galaxy. This environment is a crucial clue. Such dwarf galaxies are often factories for superstar clusters, the dense young stellar cities we explored earlier. This localization sparked a thrilling and speculative connection. Could the extreme environments within massive star clusters be the breeding grounds for these cosmic fireworks? The prime suspect is a magnetar, a type of neutron star with a magnetic field 1,000 trillion times stronger than Earth's. When these magnetic monsters experience a starquake, a sudden cracking of their rigid crust, or when they are engulfed by debris from a surrounding disk, they can unleash a catastrophic release of magnetic energy. In an instant, this energy is channeled into a tightly focused beam of radio waves, a flash so intense it crosses cosmic distances. Why would clusters be the perfect nurseries for such beasts? Because magnetars are born in the supernova of the most massive, short-lived stars. A young, massive star cluster is exactly where you find a high concentration of these stellar titans, all living, dying, and exploding in rapid succession. The dense environment could even enhance the process. A newborn magnetar might be surrounded by the dense debris of its own explosion or material stripped from a binary companion, providing the fuel for repeated outbursts. While the link is not yet proven, the logic is compelling. The chaotic, energetic cradle of a superstar cluster provides all the necessary ingredients, the massive stars, the violent deaths, and the messy aftermath, to forge the universe's most powerful magnetic engines. This transforms our view of these glittering stellar nurseries once more. They are not just places where stars are born, but potential factories for the most fleeting and energetic signals in the universe, brief, brilliant screams echoing from the hearts of their most destructive creations. But the story of stellar transformation does not end with simple blue stragglers. In the most massive clusters, astronomers have found stars that push the boundaries of evolution into a bizarre new territory. These are the blue hook stars, a name that comes from their strange position on the chart astronomers used to map stellar families. On this chart, most aging stars follow a predictable path, but the blue hook stars break away entirely, forming a sharp downward hook at the very end of a sequence. They are not just blue, they are a searing, ultraviolet blue, far hotter and more luminous than any normal star of their age should be. They have been spotted in giants like Omega Centauri and NGC 2808, and they represent the most extreme chemical and physical makeover a star can undergo. Their light tells the story. When analyzed through a spectroscope, these stars reveal a composition that is almost shocking. Their atmospheres are dominated not by hydrogen but by helium. In some cases, helium makes up more than 80% of the outer layers, a radical departure from the cosmic norm. How does a star become so rich in this heavier element? The leading theories point to processes of catastrophic loss and violent union. One possibility is that a red giant star suffered such severe stripping, perhaps from a binary companion or a close encounter in the dense cluster core, that its entire hydrogen-rich envelope was torn away. What remains is the star's naked helium-burning core, now exposed to space, blazing at temperatures that defy imagination. Another, even more dramatic scenario involves the merger of two helium-rich white dwarfs. In this cosmic collision, the combined mass could reignite helium fusion in a furious flash, creating a single, monstrously hot star that is essentially a bare, burning ember of helium. These blue hook stars are not just oddities, they are boundary markers. They show us the absolute limit of what is possible when stellar evolution is supercharged by the chaotic environment of a dense cluster. They are the ultimate products of stellar cannibalism and theft, forged in events so extreme they leave behind stars that are more chemical fossil than living sun, blazing monuments to the violence that sculpts the hearts of these ancient cities. Mapping the motion of stars in a cluster's core is like listening to a silent orchestra where every musician follows a hidden score. For centuries, we could only see their positions, frozen points of light on a photographic plate. But with instruments like the multi-unit spectroscopic explorer MUSE mounted on the Very Large Telescope in Chile, we can now hear the music. MUSE doesn't just take a picture, it captures a spectrum for every single point of light in its view, allowing astronomers to measure the precise velocity of thousands of individual stars simultaneously, creating a stunning three-dimensional map of their motions. When they applied this power to the hearts of globular clusters, the expected symphony of orderly orbits gave way to strange, discordant notes. In some clusters, the stars in the very center show unexpected patterns of organized rotation, swirling together like water going down a drain. In others, the velocity anisotropy reveals a more chaotic scene, where the star's orbits are not randomly oriented but show a distinct preference, like a swarm of bees all flying predominantly north-south rather than in every direction. These kinematic quirks are not random noise, they are forensic evidence, the dynamic fingerprints of everything that has ever happened to the cluster. A sudden, coherent spin in the core could be the lasting imprint of how the original gas cloud collapsed billions of years ago, a primordial world preserved in stellar motion. Alternatively, it could signal a much later event, a core collapse. This is a gravitational catastrophe where so many stars sink to the center through dynamical friction that the core contracts violently, rebounds, and in the process can impart a collective spin to the surviving stars like stirring a cup of coffee. Most intriguingly, these strange motions can point to an invisible conductor, the gravitational pull of a central intermediate mass black hole, or a dense knot of stellar mass black holes and neutron stars would sculpt the orbits of the visible suns around it. By decoding the precise dance of these stars, the subtle twists and flows in their velocities, astronomers can triangulate the location and mass of the hidden object orchestrating the movement from the shadows. These kinematic maps are therefore more than just charts of motion. They are X-rays of a cluster's soul, revealing the deep scars of its formation, the tremors of past collapses, and the ghostly presence of its most powerful, unseen residents. The silent symphony of stellar motion is just one layer of the music a cluster creates, for these dense cities also hum with the deepest vibrations of spacetime itself. This brings us to a future where we will not just see or measure these clusters, but listen to them in an entirely new spectrum. The upcoming Laser Interferometer Space Antenna, LISA, will open our ears to the gravitational universe, and star clusters are poised to become its brightest lighthouses. Unlike ground-based observatories that catch the final, catastrophic chirp of merging black holes, LISA will tune into lower frequencies, hearing the decades-long crescendo of binaries as they spiral inward. Within a nearby globular cluster, this will not be a solitary sound. Imagine the core of a place like 47 Tucani, teeming with hundreds of thousands of stellar remnants. It contains a vast population of tight binary systems, pairs of white dwarfs or neutron stars whirling around each other in orbits so close their periods are measured in minutes. Each of these duets emits a faint, pure tone of gravitational waves. Individually, they are whispers, but together, thousands of them create a constant, resonant hum, a gravitational chorus emanating from a single, pinpoint location on the sky. To LISA, a nearby globular cluster will not be a silent point of light. It will be a brilliant, shining beacon in the gravitational wave spectrum, one of the loudest and most localized sources it can detect. This changes everything. By analyzing the specific frequencies and strengths within this hum, astronomers will be able to conduct a census of the invisible. We will be able to count how many tight binary white dwarfs exist, estimate the population of neutron star pairs, and even infer the presence of elusive intermediate mass black holes if they are perturbing the orbits of these smaller binaries. It will be like using a stethoscope on the cluster's heart, listening to the precise rhythm of its most extreme inhabitants, objects that are often completely dark in electromagnetic light. This gravitational lighthouse effect will allow us to peer into the densest stellar environments and take inventory of their hidden machinery, revealing a dynamic landscape of death and partnership that has until now been shrouded in silence. This gravitational hum reveals the hidden machinery of clusters, but the very nature of that machinery forces us to ask a more fundamental question. What exactly is holding these stellar cities together? For one recently discovered system, the answer may be the universe's greatest secret. The Gaia satellite, mapping the precise positions and motions of over 1 billion stars, uncovered a faint, extended smudge of stars now known as Gaia 1. At first glance, it appeared to be a typical, if somewhat sparse, open cluster, but the numbers told a different, more intriguing story. By analyzing the motions of its stars, astronomers could calculate the total gravitational pull needed to keep them bound. The result was startling. The required mass was far greater than the combined mass of all the visible stars within Gaia 1. There is an immense amount of something else there, exerting a powerful gravitational grip. The leading candidate is a dark matter halo, an invisible cocoon of the mysterious substance that permeates the cluster. This single observation blurs a line we thought was clear. We have massive star clusters held together by the gravity of their own stars, and we have ultra-faint dwarf galaxies, diminutive galaxies that are overwhelmingly composed of dark matter with just a sprinkling of stars. Gaia 1 sits awkwardly between these categories. It has the stellar population of a large cluster, but the gravitational signature of a tiny galaxy. Its very existence suggests a continuum of objects where the distinction between a cluster and a galaxy is not a binary choice but a spectrum. This raises profound questions about origins. Did Gaia 1 form as a star cluster within a small knot of dark matter from the very beginning, a rare pocket where normal and dark matter were mixed? Or is this an example of a cluster that, through its long galactic orbit, managed to capture and retain a halo of dark matter from the Milky Way's vast reservoir? If dark matter halos can indeed be acquired, it would mean these structures are not static fossils. They could grow and change, gathering invisible mass as they travel, fundamentally altering their destiny and their ultimate lifespan. The disintegrating light of Gaia 1 may be the first clear glimpse of a hybrid object, a celestial chimera that forces us to rewrite the definitions in our cosmic field guide. The gravitational identity of a place like Gaia 1 is written in its stars, but that identity is not just about motion. It is etched into the very atoms of each sun. Every star carries within its light a precise chemical fingerprint, a unique blend of elements inherited from the cloud that gave it birth. For stars born together in a cluster, this fingerprint is nearly identical, a shared family signature. This simple fact has opened an extraordinary new window into the past, a technique called chemical tagging. It works because this stellar DNA is remarkably durable. Even after a star cluster is completely torn apart by the Milky Way's tides, its member stars scattered across tens of thousands of light years, they each retain that original chemical tag. They become cosmic orphans, but orphans carrying perfect birth certificates. This transforms our view of the galaxy's halo, that vast, sparse sphere of ancient stars surrounding the Milky Way's disk. For decades, these stars appeared as a random, lonely population. but with powerful spectrographs we can now read their chemical tags. The ambitious goal is to sift through millions of individual stars in the halo, searching for those with matching chemical signatures. Finding a group of stars now far apart that share the exact same abundances of iron, magnesium, sodium, and europium would be like finding pieces of the same shattered vase in different continents. It would prove definitively that those stars were born in the same long-vanished stellar nursery, a globular cluster or dwarf galaxy that was consumed billions of years ago. Projects like the Galactic Archaeology with Hermes survey are attempting this very feat, gathering detailed spectra for hundreds of thousands of stars. The process is a monumental exercise in cosmic forensics. Imagine the galaxy's halo not as a collection of random points, but as an archaeological dig site. Each star is an artifact. By cataloging their chemical compositions, we can begin to sort them into groups, identifying which relics came from the same original structure. A successful match is more than just a reunion, it is a reconstruction. By tracing the orbits of these chemically tagged siblings backward, we can estimate the size, mass, and even the orbit of their parent cluster at the moment it was destroyed. We can map where these building blocks came from and how they were assimilated. This turns the entire galaxy into a living history book. The chaotic, blended stellar population we see today is not the end of the story. It is the accumulated result of countless mergers and digestions. Chemical tagging offers the potential to reverse that process, to deconstruct the Milky Way and identify its constituent parts. It promises to reveal how many globular clusters and dwarf galaxies went into building our galactic home, which were the major contributors and which were minor acquisitions. We are on the verge of not just studying the ancient clusters that survive, but of resurrecting from starlight alone the ghosts of those that did not. The final, most violent chapter in a star cluster's story is not written in its past, but in its inevitable future. For every ancient cluster orbiting the galactic core, there is a single, inescapable destiny if its path drifts too close to the center. There, lurking in the darkness, waits the supermassive black hole Sagittarius, a star, a monster with the mass of 4 million suns. This is not a gentle end. A globular cluster on a fatal orbit experiences a force so extreme it defies all cosmic structure, tidal disruption. As the cluster approaches, the difference in the black hole's gravitational pull on the near side versus the far side becomes overwhelming. This tidal force is far stronger than the mutual gravity that has held the cluster together for billions of years. The cluster does not simply fall in. It is unraveled. First, the outermost stars are peeled away, drawn into long, streaming arcs. Then, the cluster's core itself is stretched. Over centuries or millennia, the once proud spherical city of stars is pulled into a single, brilliant thread of light, a process physicists call spaghettification. This stellar spaghetti, a line of stars millions of miles long but only a few wide, spirals inward. The stars themselves are not torn apart, they are simply separated from their family and pulled into single-file orbits around the abyss. Eventually, one by one, they cross the event horizon and vanish from our universe, their light and mass added to the black hole's grim ledger. This is the ultimate fate for any cluster whose orbit decays sufficiently. And we may have already seen the evidence. Astronomers have detected strange, thin streams of stars near the galactic center that do not trace back to any known cluster. These could be the final, dissolving strands of a cluster that was consumed in the last few million years, its last members still circling as a ghostly memorial. Furthermore, the very presence of surviving clusters on tight orbits around the galactic center gives us a unique probe. By measuring their precise paths, we can map the warped space-time in the black hole's immediate vicinity, testing Einstein's theories of gravity in the most extreme environment imaginable. So these ancient clusters, which have witnessed the universe's entire history, serve a final, profound purpose. They are not just survivors or factories or fossils. In their end, they become courageous scouts sent into the deepest gravitational wells to send back data with their very lives, teaching us about the monsters that rule the hearts of galaxies. From the violent unraveling at a galaxy's heart to the quiet chemical tags of ancient orphans, our journey through 25 strange discoveries reveals a stunning truth. Star clusters are not the simple, serene collections of stars we once imagined. They are dynamic cosmic laboratories, places where the fundamental rules of physics are stretched and rewritten in real time. Each glittering island is a living narrative, a story of cannibalism and rebirth, of hidden monsters and runaway worlds. They have taught us that stars can steal life and forge diamonds from destruction, that planets can survive supernova, and that the universe's first chapters are still being decoded in their ancient light. These discoveries transform clusters from celestial backdrops into central characters in the epic of cosmic evolution. They are the key to understanding how stars are born, live, and die in extreme environments, how galaxies assemble themselves through violent mergers, and how the most energetic events in the cosmos are triggered. The next time you look up on a clear night and find the Pleiades, that tiny, shimmering dipper, see it for what it truly is. See the blue stragglers, the potential planets, the slow-motion dance of dissolution. See a vibrant, chaotic, and deeply mysterious piece of a much larger puzzle. If you want to keep exploring these cosmic mysteries, be sure to subscribe for more deep dives into the wonders of space. And let us know in the comments which of these 25 strange discoveries about star clusters did you find the most incredible.